please take a moment to look at the pH value of everyday items. Like I said on the last slide, we can quantify the concentrations of hydronium and hydroxide ions using molarity, like we've learned in previous lectures. Molarity is equal to moles over liters. The concentrations of the hydronium and hydroxide ions, though, are extremely small, and so we have to use something new mathematically. It's called log. You'll learn the true math behind the log button on your calculator later in your math class. But what we're going to do is just use the button. What I want to quick show you is this little sliding scale on the concentration of our hydronium and hydroxide ions. Keep in mind that these are aqueous solutions, so the hydronium and the hydroxide ions are pretty much always in solution together in different ratios. But the highest molarity that we can reach is a 1 molar hydronium ion or a 1 molar hydroxide ion concentration. And this equates to our pH. If we have all hydronium ions in our solution with a molarity of 1, then we have a pH of 0. And if we have all hydroxide ions with a concentration of 1 molar, then we have a pH of 14. This represents the entire scale of pH. In the next couple of slides, I'm going to show you how to do this mathematically and calculate pH and pOH from various values that are given. Please take a moment to copy down this pH map. pH stands for power of hydrogen and pOH stands for power of hydroxide. On the last slide, I showed you that the highest pH value was 14. And it just so happens that if we add our pH and pOH on that sliding scale, their sum is always 14 as well. So this is an important concept here for us. We're going to use our log button on our calculators, and I'll show you on the next slide how to do that. But pH is equal to negative log of the hydronium ion concentration. The same goes for pOH. It's the negative log of the hydroxide ion concentration. We can also utilize a very important mathematical concept here. If we multiply the hydronium ion concentration times the hydroxide ion concentration, we always get a constant value, and that constant value is 1 times 10 to the negative 14th. So we can utilize this to solve for one of these concentrations. And if you take a look here, if we need the hydronium ion concentration, but we're given pH, we simply take 10 to the negative pH. This is literally our first time that I would accept us using 10 caret top and then the negative sign of our pH value. Or you can use your second log, but we would normally call it inverse log. All right, as usual, you need to copy down the examples. We have 4 examples tonight, so quickly copy these down. For our first example here, we are asked what the pH of a solution is whose pOH is 8.90. If we take a look here, we're starting at pH, or we're starting, at pOH, and we want to get up to pH. So we're going to use this little equation here. pH plus pOH is equal to 14. We always want to write down the equation first so we can start working with it. So we have pH plus pOH is equal to 14. The only way to solve for pH is to subtract pOH on both sides. So pH is equal to 14 minus 8.90, which gives us an answer of 5.10. You could leave it at 5.1 or you could keep the second decimal place. There are no significant figures when we're talking about pH and pOH. There are also no units for pH and pOH. So the general rule of thumb is if you start with 2 decimal places, end with 2 decimal places. If you start with 1, end with 1. But here's our answer. We would consider this solution, since it's below a pH of 7, to be acidic. Let's now take a look at the next equation. It asks us what the pH is of a solution whose hydronium ion concentration is 3.79 times 10 to the negative 6th molar. So we're over here, we're given the hydronium ion concentration and we're asked for pH. So we're going to use this negative log of the hydronium ion concentration. So we take negative log pH is equal to the negative log of the hydronium ion concentration. So we literally type it in, negative log 3.79 times 10 to the negative 6. When we do this on our calculator, which I'll show you in just a second, we get a pH of 5.42. This solution would also be considered acidic. If we look at the calculator, I took a picture of what I did. This is how we would actually key this in. We would key in the negative sign, then log 3.79 second EE negative 6, and then hit enter. And we get 5.42. Please take a moment and copy down this example. Okay, if we take a look here, we are asked now to solve the pH of a solution whose hydroxide ion concentration is 7.22 times 10 to the negative 5th molar. So we are here at the hydroxide ion and we have to get over to pH. So we have one of two directions to go. We can either go up and across, or we can go across and up, but we can't go diagonally. So what we're going to do is first go with what we're familiar with. We're going to take our negative log of our hydroxide ion concentration and then use our pH plus pOH equals 14. In the second part of the example, I'll show you the other method. So in the last slide I showed you how to calculate pH, but now we're going to look at pOH is equal to the negative log of the hydroxide ion concentration. So when we do that, pOH is equal to negative log 7.22 times 10 to the negative 5th. When we do that on our calculators, just like I showed you, we get an answer of 4.14. But we still need pH. So if we use pH plus pOH is equal to 14, then pH is equal to 14 minus 4.14. This yields a pH of 9.86. This is a basic solution because the pH is over 7. So how do we go about solving this problem using the other direction? Here we would first have to use this new equation that we haven't looked at yet, the hydroxide ion times the hydroxide ion concentrations. So let's take a look at how we would go about doing that. If we know that the hydronium ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the negative 14th, then we can solve for the hydronium ion concentration. So the hydronium ion concentration is equal to 1 times 10 to the negative 14th divided by the hydroxide ion concentration, which is 7.22 times 10 to the negative 5th. When we plug this in our calculator, we get a hydronium ion concentration equal to 1.39 times 10 to the negative 10th molar. Now we can plug this into our pH equation over here, negative log of the hydronium ion concentration. So pH is equal to negative log of our newly calculated hydronium ion concentration, 1.39 times 10 to the negative 10th. When we do that, we also get a pH of 9.86. So what's wonderful about our little pH map is it doesn't matter which direction you choose, you end up getting the same answer. Both of our answers were the same for each direction.